Dark blue? All right, so I just started the recording, so let me just go back to this. So this is the equilibrium. So we're going to do something similar for the cobalt. So what was the equilibrium for the cobalt? So it's going to be cobalt. Well, the cobalt formed a chlorido complex. Is that correct? And how many chlorides did it accommodate? And so this, we have to see a lot of these to look for some kind of pattern in them. But when we look at this, it's going to form a tetrachlorido. Now, the hexa-aqua complex is just cobalt 2 plus aqueous. And the same thing here. When we look at copper, this is actually the hexa-aqua complex for copper. Here. Going to the tetramine complex here. And so when we have copper 2 plus aqueous, it's going to be the aqua complex. Just like when we have cobalt 2 plus aqueous, it's going to be the complex. And so it's a hexa-aqua complex here. But how many chlorides are going to bind? And so we can see that here, only 4 chlorides to go to the tetrachlorido complex of cobalt. And so only 4 chlorides bind. And then we're going to get the tetrachlorido. We don't need parentheses here. This. All right, so if we add more chloride, and so we increase the chloride, then which way is this going to shift? If we increase the chloride, it's going to shift it to the right. Too much reactant, not enough product. Maintain that ratio. If we add water, now water's pure. And so you think we add water, it's going to shift it here. But when we do these Le Chatelier's shifts, it's based on concentration or pressure. So if I have, let's say, 2 gallons of water versus 1 gallon of water, is 2 gallons of water twice as concentrated? No, it's the same concentration, so it doesn't impact it. And so, but having more water around is going to reverse the shift. Yeah. Because normally when we do something like this, we don't usually show the aqua complex. Normally when we do something like this, we just go cobalt 2 plus 4 chlorides. This would be cobalt 2 plus aqueous. All the ions would be aqua complexes. And then this is going to form the tetrachlorido cobaltite ion here. And when we dilute it, we make more space. And when we make more space, it's going to favor the side with more stuff. And so here, if we're adding water, it's going to favor this because there's more particles that we need to accommodate in solution here than over here. There's only one solute particle that we need to accommodate. And so dilution is going to impact the left side less than the right side. And so by adding water, we dilute both sides. And the result is a shift here because one side's impacted more than the other. Now, if we had 5, there's 5 particles. If we had 5 particles over here, then dilution's not going to have any impact because it's going to dilute both sides evenly. Does that make sense? In other words, we look at the impact that has. All right. See what's next. What did you put for item 10? and 11. So here we have to go back in the procedure and look for what they're asking. Here's item 11. 10 must be right before that. Here it is. Record your observation on the report sheet, 10. So we're adding sodium carbonate to silver nitrate. Okay. So for 10, it's sodium carbonate plus silver nitrate. Or was it? No, yeah, silver nitrate, not sodium nitrate. So what forms here? This is double replacement, metathesis reaction. We're going to form silver carbonate and sodium nitrate. To balance this, we'll need 2 silver nitrates and 2 sodium nitrates. And we're going to have a driving force for this. Driving force is going to be precipitate. What color is silver carbonate? White. And so we should end up with a white PPT here. Okay, number 11, what do they want us to do? They want us to add nitric acid to this white PPT. So number 11, if we add nitric acid to this white PPT, nitric acid, HNO3 and sodium nitrate aren't going to react. And so this is going to react with the silver carbonate solid. And this is going to be a double replacement or metathesis or redox reaction. And what forms here? Well, we're going to form silver nitrate plus H2O liquid plus CO2 gas. So the precipitate dissolves. Silver nitrate's colorless, water is colorless, CO2 is colorless. So we end up with a CCS and a CCG. CCG is the CO2. CCS is the silver nitrate aqueous. This will be the driving force here. There's also one more driving force, which would be stronger acid, HNO3, to weaker acid, CO2. S8 at WA. So the precipitate dissolves, resulting in a CCS and a CCG. Let's take a look. That was 10 and 11. Let's take a look at 12. Account for your observations. Consider the following equilibria. Well, if you want to describe this in terms of equilibria, then I write the equations a little bit differently. And so there are different ways we can describe this particular equilibrium. One way is, I'll just write the net ionic equation. We have 2 silver ions combining with a carbonate ion. And this is going to form silver carbonate solid. In terms of Michel-Hayes type perturbation here, what we're going to do is we're going to add nitric acid. The nitric acid is going to supply H+, and we end up with 2H+, plus the carbonate yields CO2 and H2O liquid. CO2 is a gas. So as I remove the carbonate, it shifts the equilibrium to the left. So originally we precipitated it out, and now we're dissolving it by shifting it to the left. But we're not just dissolving it, we're also attacking the carbonate and converting it to CO2 and water. Did silver chloride dissolve in 13? So let's take a look at what they're asking for in 13 here. In 13, they're asking you to add ammonia to silver chloride. Did it dissolve? Yes. We should have a white PPT of silver chloride solid, and then we add ammonia. And it forms a diamine complex. We could look that up. That we end up with the diamine silver 1 ion. Yeah. So the precipitate white PPT dissolves. Dissolved. What effect did the addition of HNO3 have on the contents of the test tube? So if we add HNO3 to this previous equilibrium, what effect is that going to have? This is plus chlorine. This will be 14. If we add HNO3, we're adding H plus. The nitrate's a spectator. And that's going to react with the ammonia to produce ammonium. Ammonium is not going to participate in this equilibrium. So the number 14, we get a shift left. And what we should do is we should reform the precipitate. So we're just going to shift this equilibrium back to the left, reforming the white precipitate, silver chloride. 14. 15, what effect did the addition of ammonia have on the contents of the test tube? Um, 15. Okay, let's see what they're asking about in 15. This is 17, 16, 15 here. 15 molar. Acidify the solution. Record your observations. 14. Again, while mixing, add 15 millar ammonia until there's no longer a change in appearance. Record your observations. So it's the same equilibrium, but now we're just going to add ammonia. So in 15, we're going to add concentrated ammonia, which is going to reshift the equilibrium to the right. And so we expect to shift right, and therefore the precipitate should dissolve again. Precipitate dissolves again. (16) The solution from above, continue to add 0.1 molar Ki dropwise until you see evidence. Record your observations. So did you get in 16, you got a precipitate. You should have gotten a precipitate. And so in 16, you're adding iodide to precipitate out silver iodide. And so you should just get more precipitate. What was the color of this precipitate? Also white? All right. 17 is the temperature. Compare the color and cool the solution. So 17 was the color. So temperature is going to impact the equilibrium as well, but temperature does it differently. Temperature actually changes the value of K in the equilibrium. So we got to look, which one's favored in terms of equilibrium. Was it the same equilibrium that we were looking at before? Did you get the same colors as before when you were adding the HCl? So the hotter temperature favored what color? Red. And the cooler temperature favored what color? It was also what? Red, just a different shade of red. Lighter. Wine color. What was the color of the tetrachloride complex? Blue. Dark blue, and this was red? Yeah. Well, it's not so readily apparent, but with temperature, we shifted towards the endothermic direction. So increasing temperature favors the endo, whichever direction is endothermic. Like melting ice is endothermic. Decreasing temperature favors the exothermic direction, but this one is not so clear. And so you can leave this. You need more observations required. Yes, or they have to show the equilibrium. And so you can leave it like that. All right, any questions on the report sheet? So can you turn in your report sheet either today or you do it tomorrow or something? You just email it to me. It's fine. All right, we're going to continue the problem we were working on yesterday. So take a look at the calculation we left off yesterday. I'm just going to grab something. The calculation, the NO calculation. Fourth order one. Yeah. All right, we're going to do another calculation here. So, we didn't finish that? What was the calculation I left off with last time? Was it the iron?
Yeah, the iron.
Oh, okay. Well, I lost the notes. Were you able to solve for x? Did anybody get x? So we got, which way did we figure out? We calculated Q, right? Did we calculate Q? And we decided the reaction, Q was too small, so the reaction had to go forward. And so it was minus 2x, minus x, plus 2x, plus 2x. Is that right? Mm-hmm. And so we were left with 0.5 thousand minus 2x molar, 0.5 thousand minus x, 0.03 thousand plus 2x, 0.03 thousand plus 2x. And so we plugged it in up here and we got 0.03 thousand plus 2x quantity squared. Actually, and then another one. So we'll just raise this to the fourth. Divided by 0.5 thousand minus 2x squared. And 0.5 thousand minus x to the first. So we left all of that. And then we have to solve this for x. Was anybody successful? No. So we could try different things. One thing we might try is the simplifying assumption. What was the simplifying assumption? We assume that the change is negligible. But the problem is if we assume the change is negligible, the 2x drops here. The change is 2x, so we drop that. The 2x drops here and the x drops here. And so what results is there's no x to solve for if we use the simplifying assumption here. The other option is we do the simplifying assumption maybe to the denominator only. If we did the simplifying assumption just to the denominator, why? Because 0.5 is bigger than 0.03. And so the change, 2x compared to 0.5, is going to be relatively smaller than the change here, 2x, compared to 0.03. And so if you have less to begin with, then the change is going to be more significant. Okay? And so we could do that. Or there's another common trick that we do. The simplifying assumption is one trick. What was the other trick we do? Like in the last problem. Well, the trick we used in the last problem was reset. And so what I'm going to do is I'm just going to reset this and see if that helps. So this math looks a bit difficult. And so instead, we reset it. Now, the strategy that we use to reset it is we look at the K value. If the K is really small, it favors the reactants or it favors the product. If the K is really small, it favors the reactants. And so if that's the case, I'm going to reset it to the left because K is very small. If K is very big, I reset it to the right. So when I reset it to the left, I assume 100% reaction back to the left. So what I'm going to do is I'm going to shift all the atoms back to the left. And so I'm going to call this plus 2y, plus y, minus 2y, minus 2y. And then I look at the limiting reactant. In this case, it's stoichiometric, 0.03, 0.03, and I'm shifting it to the left. So what I'm going to do is I'm going to call 2y equal to 0.03, and I'm going to end up with nothing here, and then nothing here. And then I'm going to have 0.5 plus 0.03, and so this is going to give me 0.53 molar. And then I have y. Y is going to be half of 2y, so it's going to be 0.015. So this is going to be 0.5150 molar. And so what I did is I still have all the same number of atoms. I just shifted all of them to the left. And what I'm going to do is I'm going to just approach equilibrium from the right. Now the change, I'm going to go to the side with zeros. So this is going to be minus 2x, minus x, plus 2x, plus 2x. No, this would be molar, molar, molar. And so at equilibrium, I'm going to have 0.5300 minus 2x, 0.5150 minus x, 2x, and 2x. So now let's look at this. When I plug this into K, it's going to equal 2x squared quantity times 2x quantity squared. So this is going to give me 2x to the fourth. Divided by 0.5300 minus 2x squared times 0.5150 minus x. Now you compare the original equation here that I crossed out versus this. Which one looks easier to solve? The second one does. So let's try to solve it. The problem is trying to solve it is still fourth order. And so it's still going to be difficult to solve. But if you look at this, we're going to try the next trick, and that's the simplifying assumption. Since K is small, the reactants are favored. So we don't expect to form much product. And so the simplifying assumption is we're going to say that 2x is much smaller than 0.53, and x is much smaller than 0.515. Well, if 2x is much smaller than 0.53, that's a bigger change. And so we only really need to justify the first one, but we'll have both of them. And so if that's the case, then we're going to get 2x quantity to the fourth on top. And then the 0.5300 minus 2x is just going to go to 0.5300. We're just going to assume that 2x is such a small change, it's not really going to impact this. And the same thing with x. X is such a small change, it doesn't really impact this here. And so we drop the binomials here. Okay, now look at the math. The math is going to be easy to solve. So we know that k is 9.14 times 10 to the minus 6. 9.14 times 10 to the minus 6 times 0.53 squared. I forgot the squared there. Times 0.515 divided by 2 times 2 is 4 times 2 is 8 times 2 is 16 divided by 16. And then I'm just gonna square root that answer twice. Square root. And I get an x equal to 0.01695. I have too many sig figs, but that's all right. The reason I carry extra sig figs is when I do my double check, I minimize rounding error. So if x is equal to that, then 2x will be double this. So I'm just going to go ahead and times 2 here and see what it comes out to. 2x is equal to 0.03390. So we'll just go with that. And so this is going to be 0.5300 minus 2x, which is 0.03390. 0.4960. 0.4960 molar. This is going to be 5150 minus x. So 5150 minus x, 0.515 minus 0.01695. This comes out to 0.4980. 2x we already calculated, 0.0339, 0.03390, 0.03390. These are the equilibrium concentrations I calculated. Next, what I want to do is I want to double check my calculation. The way I do that is I just calculate the K. So this is 0.03390 to the fourth. 0.4960 squared, 0.4980. I'm off. Maybe I screwed up my calculation. Did anybody get closer? Let me double check that calculation. Hope I didn't lose it. Huh. All right. Unfortunately, I lost that document. So did anybody write down those numbers? Okay. Well, it turns out that K was off. And so there's some kind of calculation error. Okay. Oh, I needed the X. It's okay. K was off. All right, we'll just go from here. K was off, and go ahead and give me the X, Tristan.
X was 0.069.
And the 2X?
0.033909.
Okay. K was off. I forgot to justify the SA. How do you justify the SA? The justification for the SA is that the percent change has to be less than 5%. This is the calculated percent change, and it's estimated. It's estimated because we're using the simplifying assumption. And so what was the bigger change, X versus 0.515 or X versus 0.53, 2X versus 0.53? 0. On the one hand, 0.5300 is bigger. So any change on a bigger number will be smaller relatively. But it's not that much bigger. I mean, 0.5150 was 0.53. On the other hand, the change here is X, whereas for 0.53, it's 2X. So I think this is going to be a bigger relative change. And so we want to calculate the percent change based on this number here. So let's go ahead and calculate the percent change. The percent change is going to be the bigger of the two, which is going to be 2X over 0.5300 times 100%. And so 2X, we can calculate it up here. It's 0.03390 divided by 0.5300 times 100%. And so let's go ahead and calculate it. 0.0339 divided by 0.53 times 100. And the percent change comes out to 6.396%. 5% change is already pushing it. And so it's a gray, it's not set in stone. And so it's kind of a gray area, but they pushed it to the limit. So you really don't want to go beyond 5%, otherwise you're introducing too much error into the calculation. The simplifying assumption is not good. So what we say is that, oh, it's negligible, the change. And then we calculate the change. So initially we said there's no change, it's negligible, we completely ignore it. Then we calculate the change, and then we incorporate the change. And so based on initially saying the change was negligible, we came up with a change that came out to 6.4%. It's not really negligible, is it? It's significant. And so what we have is this is greater than 5%, and 5% is already too much. And therefore, we can't use. SA fails. So we tried resetting, and another advantage of resetting is it makes the simplifying assumption more likely to work, but it's not guaranteed to work. In this case, it didn't work. We tried the simplifying assumption, that failed, and therefore, what can we do? Well, we only have the method of last resort. What's the method of last resort? What is the method of last resort? Yeah, Appendix A. Appendix A. Somebody remind me, what's in Appendix A? The method of successive, tell me what the last word on this is. Method of successive approximations. AKA the guess and check method. Now we have two K equations we could use. We could use the original K equation that we didn't reset, or we could use the reset K equation. Which one looks easier algebraically to solve? I would say the second K equation looked easier. This looks easier. We'll try to make it even a little bit easier to solve. So I'm going to call that 16x to the fourth on the top there. And then down here, we'll just leave it. I'm not going to multiply out this binomial. It's going to get too messy. So we'll just leave it as is. Now, we're going to guess x and then see what k equals. We know that k is supposed to equal 9.14 times 10 to the minus 6. So we're going to try to guess an x value that when we plug it in here gives us 9.14 times 10 to the minus 6. That's the guess and check method. And so the first guess we should do is the one we figured out from before. That is x is equal to 0.01695. Well, the problem is I don't want to use that many digits because that just means punching more numbers in the calculator. And since this wasn't even correct, what I'm going to do is I'm going to call that, I'm just going to round it to 0.017. Does that make sense? So this is kind of close, but not close enough. And so our first guess is going to be an x equals 0.017. And then we're going to plug it into this equation here for k. And so I'll go 0.017 to the fourth. Let's go ahead and calculate it. 0.017 to the fourth divided by parentheses 0.53 minus 0.017 times 2 is 0.034. So minus 0.034, close parentheses, square that, times parentheses 0.515 minus 0.017, close parentheses. And what did you guys get? Oh, I see. I think I screwed it up here. I need one more parentheses. Does somebody get the answer? Okay, I'm going to convert that to 10.9 times 10 to the negative 6. We're pretty close. Do you see? It's pretty close to 9.14. We're just a little bit too big. Okay, so what should we guess next? We want to keep the numbers simple. And so I would probably guess a 0.0 what? 0.016. Does that make sense? So let's try 0.016 in there. When you have repetitive calculations like this, let's say this came up in the homework. If this came up in the homework, what I would do is I'd just use Excel to figure it out. So let's say this particular problem came up in the homework. I would go ahead and type in the formula in Excel. So I'd have my x value here, and then type in the formula here, which is equal to 16 times x, which is a1 in this case, to the raised to the fourth power, divided by 0.53 minus 2x, which is a1, squared, divided by 0.515 minus a1 or x. Actually, I'm missing one parentheses there. Close parentheses. And so I tried 0.017. 0.017 gave us 10.9. Then I'm going to try 0.016. Actually, let me delete these. This will be our strategy. I'm going to speed things up so we don't have to sit there and grind through the calculations, but on a test you would have to sit there and grind through the calculations. At 0.016, you see it's too small. It's supposed to be 9.14. We got 8.47. So what's your next guess going to be? 0.0165? Okay, let's try that. If I do 0.0165, then what is my x? 9.63. We're getting closer. I mean, it's 9.14, right? So what's your next x going to be? We're a little bit too big. So we went too small, and now we're too big. So what should your next x be? Just a little bit too big. Yeah, let's try that. 0.0164. And see what our x comes out to. 939. Still a little bit too big. Now, you know what I'm going to do with Excel is Excel will recognize a trend. So this is 165 to 164. The next one I'll try is 163. So I'm just going to drag this and just have it do it. So I go 165 to 164 to 163 to 162, and then what do I see? I'm really close at 163, but a little bit too high, and at 162, I'm a little bit too low. And it looks like, actually, let me delete all these. I was doing this earlier. So it looks like it's closer to 163 than 162. So what are you going to choose for your next guess? 1635. Okay, if I go to 1635, am I getting warmer or colder? Colder. I probably want to go to 162.5. Yeah, let's try 162.5. I'm a little bit too small, so where should I go next? 1629. Okay, let's try that. 101629. Getting close. What do you think? Another 9? 0.1016299? Give me another one. Well, it's a little bit too big, so maybe we'll try 0.016298. Let's try that. Still a little bit too big, but I have 9998, so I'm going to use Excel to go ahead and calculate those. So I'll go 98, 97, 96, 95, 94. Actually, let's go farther. Oops. 93, 92, 91, 90. So what does it look like the best one is? Here. As long as we can round it to 9.14, we're okay. So 15 would have worked okay. This one would have worked also. This one would have worked also because this one would round. This one would also round to 9.14. This one would also round. And so in this range would have been probably okay here. But this one's the best because we're at 140. All right, and so what that's going to do is it's going to give my x. Now my x is going to be 162.94. So let's go back to our calculation. So finally, we came up with an x value of 0.016294. And that means 2x will be double that. And so let's go ahead and calculate that. 2 times 0.016294. 2x is going to be 0.032588. All right, now let's go back to our concentrations here. So we had 2 iron 3 plus a mercury 2. Oh no, this is mercury 1. It goes to 2 iron 2s plus 2 mercury 2s. And so at equilibrium, here we had this is the reset. So this would be the second ice table, 0.53 minus 2x. And so this is going to be 0.5300 minus 0.032584. Ooh, not 584, 588. 588. And so I get a iron 2 plus a 0.4974 molar. This is more sig figs than I'm allowed, but we'll just carry it over because I want to double check it again. All right, this was 0.5150 minus x. And so 0.515 minus 0.016294. and I get 0.4987 molar. 4 sig figs probably, should be okay. I could go more if I'm really worried. This is going to be 2x. This is going to be 2x. And so both of these are going to be 0.032588 molar. 0.032588 molar. So now let's double check the K. As you recall, the K is going to equal the concentration of the Fe2 plus squared times the concentration of the Hg2 plus squared divided by the concentration of Fe3 plus squared times the concentration of the Hg2 plus to the first. And so this is going to be 0.032588 to the fourth divided by 0.4974 squared divided by 0.4987. And what do we get? I get 9.1405 times 10 to the minus 6. And so it agrees. And so we're okay. The actual value is 9.14 times 10 to the minus 6. The given value. All right, any questions on this? Okay, so let's take a look at chapter 15. That was pretty much in chapter 15. What we do is these Chem 1B style equilibrium problems using ice table. And so let's take a brief look at the homework problems here. So homework problems start off with writing equilibrium constant expressions, Kc, Kp, and Keq, which is the thermodynamic one. So we just need the balanced chemical equation. And so we have an equation like this. We could do this. These are gases. So for gases, the thermodynamic equilibrium constant is Keq, stands for the equilibrium constant. And Keq is equal to Kp for gases. But they're asking for Kc. It's okay, we can get Kc as well. But in this case, Kc and Kp are not the same. Sometimes Kc and Kp are the same numerically. Like over here, in this equation, Kc and Kp are the same. And the way I can tell is by looking at delta N of the gas. If I have 2 moles of gas on the left and 2 moles of gas on the right, then Kc and Kp are numerically equivalent. This is the reaction we looked at yesterday. It's just the reverse, NO. Fortunately, NO is highly unstable. This equilibrium is heavily favored to the right. So, NO is not stable. Over here, Kp and Kc are not the same because over here I have 3 moles of gas on the left and 2 moles of gas on the right. So delta N of gas is not equal to 0, so Kc and Kp are numerically different. So when you calculate K using delta G, that K is Kp. And if they want Kc, then we're going to have to do an additional calculation to get Kc. Did I write the equation for that on the board before? Yeah, I think so. All right. However, the equilibrium constants are really based on activities. And so if we have a solid in there, the solids have an activity of 1. And so we use 1 in the equilibrium expression. And so if I write the Kc for this is just going to be the concentration of Zn2 plus times 1 squared divided by 1 times the concentration of silver ion squared. And so pure solids show up as a 1, and pure liquids also show up as a 1. So if I have H2O liquid, I'd have a 1 as well. So when I have gases, I have a choice. I could do Kp or Kc. No, but what if I have mixed? So let's take a look at a mixed scenario here. So if I have something like calcium carbonate, solid, plus 2 HCl, this is going to go to calcium chloride, plus H2O, liquid, plus CO2 gas. Then if we do a Kc for this, we're going to have an aqueous solutions. HCl is aqueous, calcium chloride is aqueous. But CO2 is a gas, and the gas is going to be in a different part of the container. And so we can get the concentration of the gas, and we can get the concentration of the liquids, but the numbers are going to be kind of funny because the gas is in a separate container. And so what we have here is we have KEQ. In this case, KEQ is not equal to KC, and it's not equal to KP. KC and KP work if we have all gases. You can use either KC or KP, or if we only have solutions, you can use KC. But neither of those will work because we have a gas here. And so what KEQ is equal to is it's equal to the activity of calcium chloride times the activity of water times the activity of CO2 divided by the activity of calcium carbonate and divided by the activity of HCl squared. Then we know that the activity of a solution is just approximately its molar concentration. The activity of water, which is a pure liquid, is 1. That is, its concentration doesn't change. It's still 100% water. The activity of a gas depends on its concentration or its pressure. In thermodynamic, this is the thermodynamic equilibrium. It's going to depend on its pressure. So this will be the pressure of the CO2 divided by the activity of calcium carbonate, which is 1, and divided by the activity of HCl, which is going to be the concentration of HCl squared. And so we just get calcium chloride times the pressure of CO2 divided by the HCl squared. KCs are all concentrations, KPs are all gases. This is mixed. And so this is neither KC nor KP. So this is just generating the expressions. This is products over reactants. That's it. Here you'll have to convert, between KCs and KPs. Here they're asking for KC, but they give you KP. Also, this one we have to add up equations, like Hess's law. When you add up equations, you have to multiply the K's. You don't add up the K's. Energies like delta H and delta G, we add up. In this next series of problems, we set up the ICE table and we're missing a piece of data. So if you look at number 18, number 18 is set up like this. And so the next series of problems, you'll have something where it's like a 2A plus a B goes to C, 2C in this case. And they tell us how much A initial we have, and B initial, and C initial we have. And then they do a measurement for the B at equilibrium. And so they tell us how much B at equilibrium we have. And then what we have to do is we have to fill in the rest of the ice table. So it's like a little puzzle. And so what are we missing? We're missing x. We don't know what that is. This is minus 2x. This is, oh, actually, it's got to go plus. It's got to go towards the 0. We can't go below 0. Can you lose anything beyond 0? So we can't have a minus. It's got to be a plus. And therefore, this has to be a minus. Can we figure out what x is? Yes. We can figure out what x is because 0 plus x gives us b, and they tell us what b is. So once we know what x is, then we can figure out the rest of this. And so we can just fill in the rest of the table. Once we fill in the rest of the table, then we know the equilibrium concentrations, and we can calculate the numerical value of K. This will be the numerical value of Kc. We just plug in the equilibrium concentrations here. So this would be C squared at equilibrium divided by A squared at equilibrium times B concentration at equilibrium. So it's just figuring out the missing parts of the table and then calculating what the equilibrium concentrations are, and then determining what K, the value of K is. And so that's this whole series of problems like this. There's parts of the table that are missing, but you can fill it out. Let's take a look at number 21 here as an example. We're for Monday's lab, we're starting a chapter 16 lab. And so you don't have to prep your notebook for Monday. We're just going to go through it together. In fact, I was going to try to start chapter 16 today, but I'm not going to have enough time. I'm just going to try to finish up chapter 15. And so today or tomorrow. I'm not, actually tomorrow. Maybe I'll talk at the beginning. Finish up. Oh, tomorrow's Friday. Oops. Monday, sorry. Monday. All right, so this is like filling in the blanks of the ice table. So this is number 21. I don't have enough room here, so I'll just rewrite it. They forgot to write the state. What is the state for the iron 3 hydroxide? Solid. That's some typo. Plus 3H plus. It's going to yield iron 3 plus 3H2O liquid. Compute the equilibrium concentration of iron 3 plus at pH 7, i.e. H plus equal. Are you familiar with power functions? This is the power of the H plus concentration. And so the power is just the exponential here, 7. It's actually the negative power. Power function is good. It's the negative power. Because the pH is 7. Actually, in power function, we got to worry about the sig figs. If the H plus is 1.0, then the pH is 7.00. It's 7.00 because 7 is the power. And the 0.00, these are 2 sig figs here. The 7 is not significant. Okay, this is not a sig fig. Just like, do we count the 7 here as a sig fig? No, and therefore we can't count this 7 as a sig fig. And so this is 2 sig figs here. And so everything after the decimal point is significant. So that's 2 sig figs there. But they give us the H plus concentration. Now, the situation is this initial or equilibrium? And so we have to read this carefully. They say compute the equilibrium concentration for Fe3 plus at pH 7. So what happens is if we start off here, 1.0 times 10 to the minus 7 molar, then there's going to be a change. And if there's a change, then it's not going to be at pH 7 any longer. And so what this means is it has to be equilibrium. It has to be at equilibrium because they're saying at. And so let's go ahead and make the table. Now, the funny thing is this. What is the activity of a pure solid? 1, it's 100%. If you have, let's say I have 10 grams of gold and I remove 5 grams, and now I only have 5 grams left over. Do I have, do I still have pure gold? Is it half as concentrated? No, it's still 100% gold. And so this, for solids, the activity doesn't change. It never changes. So we don't include the solids here because it just stays 1. And the same thing with liquids. With pure liquids, we don't have in the ice table either because it's just 1 all the way down. And we're not going to deal with it. Actually, there is, the concentration of pure water is, I'll talk about that later. And so pure solids and pure liquids, we leave out of the ice table. And therefore, we're only looking at aqueous and gases. In this case, we just have aqueous. And so they're telling us the H plus concentration at equilibrium is equal to 1.0 times 10 to the minus 7. And so pH 7 is special. Do you know what's special about pH 7? pH 7 we call neutral. And we'll talk about why later. And so we need the rest of the table. Fortunately, we don't have to get the rest of the table because all we need is, there's only one unknown here. If there were multiple unknowns, then we'd need the rest of the table. But in this case, we don't. We just need to figure out K. Now, K is just going to equal the iron 3. And so in the K expressions, I'm going to omit pure liquids and pure solids as well. I'm not even going to bother writing the 1 out. And this is going to be H plus cubed. And so I know what my H plus is, so this turns out to be quite simple because they give me my K. The K value is 9.1 times 10 to the 3. Plug that in here. And then I plug in my H plus, cube that, and then solve for Fe3 plus. And so this turns out to be a pretty straightforward problem. All right, I'm out of time, so I'll stop here.